The modern iteration of matrix theory was conceived of by Arthur Cayley in his 1858 paper, A Memoir on the Theory of Matrices. Wanting to find a tool that could handle the composition of linear transformations, his key turning contribution was that he treated arrays and systems of equations as a singular structured object. He built foundations further than this, finding processes such as addition, matrix multiplication, and scalar multiplication, as well as establishing the notation and concepts that underpin matrix theory. A matrix, in its essence, is defined as a rectangular array of scalars. For a matrix of dimensions m by n, the rows are the m horizontal list of scalars, and the columns are the n vertical lists. A specific element is denoted as aij, where I is the row index and j is the column index. For example, the element A24 resides in the second row and the fourth column. Core operations build upon this structure. Matrix addition is performed element-wise, where corresponding entries aij and bij from matrices A and B are summed. Scalar multiplication involves multiplying every element within a matrix by a constant value k. Matrix multiplication is a more complex but fundamental procedure. For two matrices A and B to be multiplied, the number of columns in A must equal the number of rows in B. The entry in the ith row and jth column of the product is computed as the dot product of the ith row of A and the jth column of B. A pivotal related concept is that of the matrix inverse. For a square matrix A, if there exists a matrix B such that their product in either order yields the identity matrix I, that is, AB equal to BA equal to the identity matrix, then B is the inverse of A, denoted as A to the minus 1. Here is an example of matrix multiplication. The first row of M2, 1, 2, and the first column of M1, 5, 7 combine as the first element in the resultant matrix. So 1 times 5 plus 2 times 7 is equal to 19. Likewise, in the second element of the resultant matrix, the first row of M2, 1, 2, is used again, but instead the second row from M1, 6, 8 is used. Then, moving to the second row of the product, the same elements from matrix 1 are used for each respective column, but instead the second row is used from matrix 2. This brings us to a special and highly structured class of matrices, permutation matrices. The permutation matrix is a square binary matrix that has exactly one entry of 1 in each row and each column, with all other entries being 0. Its relevance is direct. It provides a concrete matrix representation of a permutation of the order of n elements. Multiplying a vector by a permutation matrix permutes the vector's entries according to that specific arrangement. A key property of a permutation matrix P is that its inverse is equal to its transpose. That's P to the minus 1 is equal to P transposed. This categorizes it as an orthogonal matrix. In cryptography, permutation matrices are employed to introduce diffusion, a property that spreads the influence of plain text bits over many ciphertext bits. They serve as linear transformation layers in block ciphers, such as AES and DES, to scramble data positions without altering values. Because permutations matrices are orthogonal and efficiently invertible, they enable fast decryption with minimal computational overhead. Moreover, their deterministic structure ensures that the transformation is both reversible and efficient, making them ideal for cryptographic algorithms that require both confusion and diffusion. We now arrive at the core problem, counting matrix involutions, specifically among permutation matrices. A matrix involution is defined as a matrix that is its own inverse, satisfying the condition A squared is equal to the identity matrix. For a permutation matrix, this condition translates to the corresponding permutation being its own inverse. Combinatorially, a permutation that is its own inverse is called an involution. Its structure is restricted. It can only consist of fixed points where an element maps to itself and transpositions where two elements are swapped. Our objective is to count the number of such involutory permutations, or equivalently, involutory permutation matrices, for a given size n. Let this number be denoted by I bracket n bracket. A recursive formula provides an elegant and efficient method for calculating IN. The logic follows from considering the fate of the last element n. There are two, and only two, possibilities. First, element n is a fixed point. In this case, the remaining n-1 elements must form an involution, which can happen in in-1 ways. Second, element n is part of a transposition. It can be paired with any of the other n-1 elements. Once this pair is fixed, the remaining n-2 elements must form an involution, which can happen in in-2 ways. This gives n-1 multiplied by in-2 possibilities for the second case. As these cases are mutually exclusive, the total number of involutions is the sum. In is equal to in-1 plus n-1 multiplied by in-2. The base cases are intuitive. I0 is equal to 1 for the empty permutation, and I1 is equal to 1 for the single identity permutation. My code for CA3 implements this recurrence directly. The input is the integer, n, and the output is in. The algorithm uses dynamic programming, iteratively building the solution from the base cases up to n, which results in a highly efficient computation. The code structure mirrors the mathematical recurrence exactly. We initialize a list, dp, to store the values of I0 through in. Starting from the base cases, we iteratively compute each subsequent value using the recurrence relation. The final result, dpn, gives us in with optimal efficiency. While the recurrence is excellent for computation, an explicit formula offers deeper combinatorial insight. This formula is in sum starting from k is equal to 0. On the numerator, you have n factorial, and on the denominator, you have 2 to the k multiplied by k factorial multiplied by n-2k factorial. This summation accounts for every possible number of transposition k in the involution. The terms are decomposed as follows. N factorial over n-2k factorial. This begins as the number of ways to choose and arrange 2k elements from n to participate in transpositions, 2 to the k. This divisor corrects for overcounting within each of the k transpositions. We are indifferent to the swaps AB to BA, so we divide by 2 for each pair. K factorial. This divisor corrects for the overcounting of the order of the transpositions themselves. The set of swaps AB, CD is the same as CD, AB. The remaining n-2k elements become fixed points. This explicit formula is a sophisticated adaptation of the binomial coefficient, tailored for counting pairings rather than simple subsets. Now let's bridge the explicit and recursive formulas with a mathematical proof. We begin with the explicit formula. Let's define each term in this sum as the following, so that in is simply the sum of all a and k values. We want to show that in is equal to the recurrence formula. Finally, we can show that in minus 1 is equal to the following sum. If k is greater than or equal to 1, we compute this difference. Now, using the factorial property, we can simplify the brackets to the following. Using this, we end up reducing to the following expression. Now we can look at n-1 times a term from in-2. So ank minus an-1k is equal to the following. Summing over all k, we end up reducing to the following. Therefore, in is equal to in-1 plus n-1 multiplied by in-2. This proves that our explicit formula, the combinatorial sum, indeed satisfies the recurrence we use in our code. The mathematical consistency between these two forms reinforces the correctness of both approaches. We traced the journey from Cayley's foundational matrix theorem and then moved on to permutation matrices. We then moved on to the matrix involution problem, discussing the recursive formula and the explicit formula, decomposing it. And then we also showed that the explicit formula satisfies the recurrence formula, confirming that both methods solve the same problem. This exploration illustrates how clear definitions and logical decomposition can yield multiple pathways, both computational and combinatorial, to the same mathematical solution. Finally, here are my references.